Thank you. Hello, everybody. Thank you very much for joining us. I'm here with my colleague, Ken Keller, and also our National Technology Director in our area, Dan Walks, who's available, and we'll have technical point of contacts available. I plan at the end of each item to open first to the technical points of contact. I think I'd like to suggest that the questions be either put in the chat or come later on when we're through with the 5 presentations. We'll have 5, not 6. There may be one listed on the index that is not going to be covered. I think that we won't do 5.1 just for the people who run the show.
Frank, Nick is here now, just so you're aware.
Hello, Nick. I'm just sound testing. Are you available?
Yes, I am. Thanks, Frank.
Thank you. Welcome. Okay, I'm going to start up by I'm welcoming everybody who's taking the time to listen in. This is an exciting area. We're covering two areas in the IRPs, the accident tolerant fuel area and advanced reactor fuels. I have to tell you that because of the uncertainty of the current budget situation, we may further have to limit, restrict, or shorten what we're doing. So there is a big funding uncertainty above us, as you know if you've looked at the budget of the House and Senate. In both our areas, both ATF and advanced reactor fuels appear to be severely limited, but we hope that that won't be the case. As a matter of fact, our optimism is being shown by these set of NEOPs and integrated research proposals, IRPs. We'll go in the order. I'm going to do cover 3 areas that are in the accident tolerant fuel area. Then I'll turn it over to my colleague, Ken Keller, and we'll try to make this interesting. I'm going to begin with an IRP. It may not be the order it was shown, but I'm beginning with IRP-FC-2. Well, let me go forward. Oh, on this slide, I'm just showing you what we did last year when we were very limited in funding. We had 2 very important areas to accident tolerant fuels that we covered. And this is just giving an example. If there's anybody you want to talk to who can tell you how hard it is or what the process is and whether they would recommend doing it or not doing it, these are very successful awardees, and I'm sure any of them would be glad to assist or help you. Okay, this is what we'll be covering today in the order. And so we'll have the contacts at the very end of the presentation. I'll have a contact sheet, which will give you, the email addresses of everybody that you're hearing today. Whoops, wrong direction. Okay, no, where are we? Okay. Okay, this is the first one I want to do. The first one I want to address is ATF cladding tests in the MIT pressurized water reactor. This is an IRP, which means, excuse me. I was doing so well. Okay, here we go. So the first IRP, since this is a rather large one, it could be large and it could be for a significant amount of time. This is one of the only places where we indicate an area that we wish to use. This, thanks to the cooperation of MIT, they have a water reactor, a research reactor with a pressurized water loop. And since the ATR is down for a while, and we don't have other advanced facilities with loops available to us, this looked like a very interesting area. And so one reason it's important to the ATF is that up to now, we get the combined effect of coolant and concept when we put the lead pins in commercial reactors. And I think we're in about 8 reactors, which is the good news. but of course we can't play around with the adjust the reactor coolant, because there are some benefits that people have told me in the past, and that's one reason behind this. I remember we sent some people to various utilities, and at least one, and I think it was several, said, you know, the ATF concepts maybe can permit us to do something with the coolant that could reduce what makes the steam generator end of life. Maybe, you know, affect the crud, or affect even the cladding concept, whether it has a coating or it's a different type of material. As you know, we have coated pins, we have silicon carbide concepts, and feed crawl. So we have a lot of possibilities. And so one thing I would say is that this is really looking into things that might be directly useful to the ATF concepts. And so I would strongly urge contact with, among others, certainly the MIT people running the loop, as well as our National Technical Director, and the lead person here, Nicholas Wolstenholm. Sorry, Wolstenholm, excuse me if I mispronounce it. But you can contact any of those people, and should, in my opinion, because this will be judged and on how applicable it is in the minds of the loop, of the vendor concepts. You know, we'll look at all of those. So it's a very exciting thing. And as I said, it's to me what you can do with the coolant as it affects the clad concept. And some of the concepts, they're not yet sure of whether coolant adjustment might be valuable or not, because in the reactor, of course, there's radiolytic effects that out of loop aren't easy to study. So this is a real opportunity. Okay. It's not studying fuel and fuel cladding. That's important, because we may not put fuel in what we put into this loop. Some of the ideas here, I'm going to go back and turn it over very soon. I'll show you the ideas. This whole presentation is available. So, and if you don't have it and want to get it, just send me an email. Okay. This is the time that we that we envision. It's extended. It also hinges on the project duration. And of course, it's very important to point out that if your proposal needs some modification to the loop to serve your particular proposal, you should be talking to the loop people to find out what part of your support to them is necessary. That's not ruled out. I can't just give them money to do something, but it's important that if it's required to make an accepted proposal operate, you know, instrumentation or other factors of the loop that interface with yours, that's an important condition. To leave a lot of time, I want to turn over now to Nick so he can tell you. I'd like him to discuss what he's looking for, what's important in his mind to the outcome, and the type of metrics we'll look at when we get letters of intent. Nick, please take over. You've got whatever time you need, 5 or 10 minutes, easy.
Okay. Thank you, Frank. Can you hear me?
I can.
All right, excellent. I'm trying to turn my camera on, but let's just say my computer recently installed an update and things aren't going well. So I guess you just get my voice today. Sorry. Yeah, just give you a little more background behind the motivation on this. You know, of course we have the pressurized water loop at the advanced test reactor that we've been using to test fuel samples. ATR is not running right now. They are currently undergoing their core internal change out to replace the beryllium and other things. I will say that that's actually going well, and we expect ATR to be operational again probably before these you know, these NEUPs and IRPs would even be awarded. So the motivation for saying, hey, let's do something with MIT is not necessarily that we don't have a good in-reactor loop. it's a little bit different, actually. Really MIT excels in offering what I'll call an affordable way to do in situ instrumentation. They have a long history of that, and the layout of their reactor is very conducive to it. And so I think one of the things we're interested in here is proposals that include live instruments where appropriate and when those suit the data objectives. The other thing that's causes us to say that MIT is a good place to have proposals submitted for is because at ATR we've got a whole bunch of people all kind of I don't know, piled into the same loop. There's a lot of multi-program considerations going on. And so doing specific cladding chemistry studies, for example, doesn't just affect one specimen, it affects many. And so really, I guess what I'm trying to say in summary is that this was strategic, right? We are not asking for this just because MIT is at a university. We're asking for it because it's a good fit for some of these data objectives. Along those lines, there's a few things I want to emphasize. This call is for in-pile behavior, but we expect that it could be paired with out-of-pile comparisons, as well as simulations, obviously, and other analytic studies to elucidate what the in-reactor effects are. The call is nominally for accident-tolerant fuels, but proposals could consider some overlapping research areas, perhaps such as channel boxes or control rods that are of an accident-tolerant nature. So that would not be nominally excluded. Of course, partnerships are encouraged. One other note I want to make is that MIT's NRC license does not permit fissile material. And so this is, at least in an isolated loop, a flowing loop like this. So this call is not about fuel. This is not about fuel or the fuel cladding interaction. This is about cladding behavior and cladding coolant behaviors. But I should note that other forms of nuclear heat could be used to stimulate certain effects, such as a gamma heating surrogate. Shown here on this screen are just some specs about MIT's water loop. I won't go through this in detail, except to say that they have a really nice spectra that's fairly representative of an LWR. The flux is pretty good, and they operate a fair number of days each year. Because it's representative, but not necessarily accelerated, I think what that means is in order for the data objectives to be accomplished within the time frame of this IRP, we really are looking for proposals that create impactful data in the lower fluence or the lower exposure regimes, right? It would just take many years to get to a very high DPA in MIT, and that's probably not going to fit into the proposal time frame. Other than that, you can put a few specimens in. There's other details there. You can see those as you wish. Frank already talked about this, a really notional example schedule of what we envision such a proposal would look like with designing and fabrication, something on the order of a year to a year and a half of irradiation, followed by some post-irradiation exams, final reporting. So because that's pretty compressed for an entire irradiation campaign, I would say we're focused on data outcomes that can be accomplished with online instrumentation and at lower fluences, and perhaps with limited PIE. And the last thing I'll mention, Frank already said this, but I'll just reiterate, is that strategically, we've talked with a couple of people at MIT who are experts on using and designing tests for this loop, and they have committed to abstain from writing their own proposals so that they can be available to help consult on your idea for this one. So even though I think I'm listed as the technical point of contact, there's really some co-technical points of contacts at MIT. So if you, I would encourage you to reach out to me, and we'll coordinate a discussion to talk about your potential proposal. So that's it.
Thank you very much, Nick. I think it's important to say that in no way is this meant to substitute from capabilities that we have at the national labs. it's a complementary activity, and I'm hoping that that's obvious. Dan Wachs, our National Technical Director, also was involved in setting this up. Do you want to say a few words, please? Unmute. Did I lose you, Dan?
It still shows he's a panelist, but it shows that he's muted. Dan, if you're talking, we can't hear you.
Can you hear me now?
Yes.
Yes.
Oh, okay. I don't know what happened. It asked me if I wanted to be unmuted. Yeah, thank you, Frank. I appreciate it. I'm excited about this particular project for a lot of reasons. I think it offers some terrific technical opportunities that help the campaign, but I'm also very interested in expanding the exposure of students and faculty to opportunities to conduct irradiation testing in high-end irradiation testing facilities. And so we think that's a critical skill set that needs to expand in the greater community. So I'm looking forward to seeing the teams that put together for this and what kind of great ideas come out of it.
Thank you very much, Dan. As I said, we have a lot of hope for this. There is a problem with the short time, so that has to be considered, obviously. But hopefully, with I think instrumentation has made major advances in the last 20, 30 years. So that's also a good opportunity. And of course, this may complement some tests that are being done by some of the vendors under our program, which is why I would also encourage contact with some of the vendors whom have claddings that are near term as well as longer term. Okay, now I'll switch to the next one. Thank you very much. Okay, this one still keeps Nick involved. He's really one of our go-to geniuses, and so I'm very pleased to keep him involved. The idea here is this is kind of more like let's think about the future as well as the present. There are some LWR concepts being considered for the future. As you know, right now one only knows obviously about 2 or 3, but we were thinking that maybe some of the things we're developing now may have validity to other concepts that are new. The 2 obvious ones are shown here, but they also someday will be quizzed when they go through licensing or as part of their licensing on, beyond design basis accidents, which of course the small reactors may have much less of a situation to be concerned of and may not even be a licensing issue. But some of the concepts, the cladding concepts that we're considering, specifically coatings, let's say, might be of interest to them. And so this is kind of a really look forward to see. And maybe there's some small concepts that don't, in my opinion, don't even have water, but have surfaces that also in a beyond design basis accident may get higher temperatures than stainless steel or Zerk is meant to take. So this is a very broad one. And let's see what I'll show before I turn it over to Nick. Okay, I'm gonna turn it now over to Nick right away, so he can give an idea, because we put this together very quickly, and so I'd like to hear his idea of how he thinks this might be useful, interesting, etc. Okay, Nick.
Thank you. Yep. Thanks, Frank. Can you hear me?
Yes.
Excellent. And thanks for your kind words. It's been a while since I've been called a genius. I don't think my wife would agree, but
well,
hey,
tell her to listen in.
Okay. Even though we put this call together pretty quickly, this is actually a thought experiment we've been dealing with for a very long time, and that is,
I don't hear you now.
Many people, myself included, think that one of the prominent pieces of LWR future includes Google plant and a GE Hitachi concept. And the thought is, what can we do that's beyond the UO2 zircaloy baseline system in terms of the fuel design and the fuel behavior, or even just the fuel data, that would be more optimized for these types of plants, right? Obviously, these types of plants have different design basis accident evolutions, and certainly have different thermal hydraulic regimes, and just I don't know, in general, the design space for electrical generation for them is a different optimization problem. And so, you know, we brainstormed upon ATF technologies. Frank pointed out coated zirconium alloy, or perhaps other FECROLs, silicon carbide composites, maybe even fuel geometry modifications and thermal hydraulic optimizations for SMR applications. So this is a little open-ended. The challenge is think of an innovation to research in the fuel design that somehow increases the value potential of this next generation of SMRs. Let's see, what did we write here? So, you know, one might even think about what I'll call a phase 1, phase 2 strategy, right? I think we all know that once SMRs are starting to get on the grid, which hopefully is going to be in the next few years here, I believe it will. Perhaps there's a fuel design that's optimized for a retrofit application to support a power up rate, for example. Or perhaps there's a fuel design that supports a second generation design iteration and an even more advanced SMR. So use your imagination and come up with something that's credible. And I'm really excited about this one. I think this one will be fun. It should go without saying, but I'll say it anyway, that obviously a partnership with an SMR designer or a fuel designer would be encouraged on this type of proposal. These are the normal smaller price tag NEUPs, not an IRP like the last one we were talking about. So we're not necessarily imagining an in-reactor irradiation. Although who knows, maybe a few years from now we'll have an IRP for that as well. But for now, we're really imagining things that would be lab work and analytic studies, modeling, design studies, that kind of research. So out of pile testing to support those types of things. That's it. Back to you, Frank.
Okay, thank you. And I'll open it up again to Dan Walks. Unmute yourself.
Okay, can you hear me?
Now.
Yes.
Can you hear me now?
Yes.
Okay, got a little faster that time. Yeah, so just to reiterate some of the points that Nick's making, I think a lot of the SMR community is prioritizing getting their plants licensed and on the grid. And I think, as we've seen in all reactor technology, the version 1 is not the best version of itself, and it will mature over time. And fuel's a clear place to make enhancements. And so we want to start the innovation process here and looking at next generation ideas. I think many of the reactor vendors, you'll notice they describe the lack of innovation in fuel as a feature. I think in the future we need to fill that gap, and so this is kind of the beginning point for that effort. And obviously, the experiences we've developed as a collective university, laboratories, industry, and NRC through the development of ATF are great leverage points to help move this forward. And so we're anxious to see what kind of teams can form and what kind of ideas will come out of it. Back to you, Frank.
Okay, thank you. I'm going to move on to the third. I may have time for questions after this one. As I showed you earlier, last year we only could do 2 because of the money concerns. We decided to focus just on an advanced area for ATF, namely when you get into the very high burn-up and high enrichment regime. But this year, even though we don't have much more money necessarily, oh well, we'll see. This is an area that we had to drop a couple of years ago on accident-tolerant control rods and other materials that are not included in ATF up to now, but are important. Accident control rods are important, in my opinion, from accident tolerance concerns, but they haven't been in the formal program. So this is kind of a foot in the door. Of course, it's going to be important because things have been done. Obviously, the vendors have concerns about this. We've had some small business areas in this area. So this is one where if you're interested, you'll want to talk quite a bit with Mike Chidoso of Brookhaven National Lab, because this is kind of what he had. You know, I'm going to let him explain his thoughts. But I'll say, if you do this, we're strongly encouraging that you find out what has been thought of and done, because there obviously, you can imagine, silicon carbide is part of the fuel part of the program, and but as you know, there are people interested in using silicon carbide for more than just fuel, and so clearly in control rods, you know, if you want to make them accident tolerant, it's a problem of materials, new ones, the materials that do the control. You know, it's across the board. It's quite broad. So I'm going to turn it over to Dr. Chidoso, who's been knowing about this for years, and here's his chance to get some input.
Thank
Mike?
you, Frank. So I think Frank pretty much covered most of the important points on this already. Again, the focus with the ATF program has been on fuels and cladding, but there's been a recognition that, you know, if the fuel holds up, but everything else around it slumps and or melts, you're in worse shape than you're no longer accident tolerant. So what this proposal is really trying to get back at is, what can you do in terms of materials and or designs for control rods that can increase their accident tolerance while obviously still maintaining everything that you need the control rod to do. So it's not just the control rods, it's control rod guide tubes, it's grid spacers, core support plate that also are subject to lower temperature limits than the fuel is, and is desirable to see whether some improvements can be made there. That, again, one of the key words here is the functionality of both of those systems. As Frank has said, it's very important that there be a consultation and a recognition of the work that's being done in this area. As he mentioned, there is interest on the parts of NEI and of some of the vendors and EPRI, and in the international community. So it's a broad scoped kind of thing that complements the accident tolerant fuels to make a much more robust system than it is right now. I think that's all I could say right now.
Okay, and I would add, just from what I've been following in some of the smaller other activities, you know, when he talks about, as Mike has just said, other materials, for example, the interface of the controls in the reactor and the materials of the accident tolerant control rod. You may have metal interfacing with a non-metal material. So there's a lot of ideas to find out, and get back to Mike, because he will be able to try to get you in touch with people who have been working on this. There has been some R&D, but also money limited. It hasn't grown as much as I would like to. Okay, we're at the point. We got a lot quicker than I planned, because I don't like to talk too much. I'm not good at that, at least when the world is watching. So I would like to open this up. I looked at chat, I didn't see anything, but if there's anybody on who can either raise their hand or get recognized, I think we can have 10 minutes of questions or so. Before I switch over to Ken, I just want to open it up if there are any questions from the outside that people want to verbally give right now, if that can be done by the people who run this.
Okay, Frank, I think we have some questions in our question panel, and let me read some of those questions to you. The first question is regarding FC 2.1. What is the technical readiness level requirement?
Okay, that's to you, Nick, on next generation fuels for SMR application.
Yeah, that's an interesting question. I honestly hadn't thought much about it. I don't know that there is a requirement. I mean, you know, I think in our world we have an affinity for things that, you know, have at least been demonstrated in the past with some level of proof of principle. I think that brand new, like I've never heard of this fuel design before, things are might be interesting, but we might be a little hesitant on those. But I don't know. I don't think there's actually a real requirement. I think that this is a creative exercise. And I think that the risk and reward proposition needs to be balanced. If something is quite novel indeed, then you know, there would need to be a strong value proposition for it. Whereas if something were more mature and more of an evolutionary innovation, it would need to you know, probably demonstrate that it's more likely to succeed. So that's a very vague answer, but I don't think there is a requirement.
Well, that's a good question that can be pursued, you know, as you prepare, if and you prepare a proposal. I think that's great. Anything else?
Yes, Frank, we do have another question, and that one is for FC 2.2. So are there any DOE reports or review papers that can be read to understand the state of the art here?
I'm only aware of small, you know, what we call small, you know, the small proposals. What do you call
SBIRs.
SBIRs. There have been a couple, and I say if you contact Mike, so we can make you aware. You can contact the people. You can contact the vendors. I would suggest you could contact the vendors and see what they're interested in, because again, showing a relevance is strongly encouraged. So that would be one way to look into it. As far as DOE reports, in my many decades, yeah, I'm sure we've thought about these. There are other programs, you know, in the past, NGNP, there's been gas reactor, you know, and certainly every program we had worries about control. But in this one, we're thinking of applicable to the current existing concepts primarily.
Yeah, I think just to follow up on that, I did a presentation at an EPRI meeting on some of the neutronics work on advanced control, or on different materials for control rods. And CREEPI is interested in some of that as well. So if you contact me, I'll see what of that I can provide to you, as well as what Frank said from some of these SBIRs.
You know, Mike, you just reminded me something that I forgot to say. In addition to whom we've talked about contacting, and you know, and partnership, that could include NRC. It also could include EPRI. They have done a lot of thinking. As a matter of fact, even on the other items we discussed, you know, like coolant clad. I know that's a priority consideration at EPRI. I just forgot to mention it. So certainly they might also be a good contact. And again, Mike and the others also know about that. So I appreciate the question and the answer in particular.
Frank and others, I just want to remind everyone that the way that we take care of this NEUP program and the CINR FOA is to make sure that all this information and any conversations are filtered through the NEUP at inl.gov address. That way we can better get that information out to the community and provide the same information to all applicants. So just want to put out that reminder as we're chatting.
No, that's very important. Thank you, because I was just looking for near term, but obviously, and the good news is that questions here are heard by everybody, but otherwise, as was explained, questions, even if they're after this, will be documented so that everybody can benefit. We'll try not, you know, we don't want to favor any particular concept. Okay, anything more before we go on?
At this point, Frank, there are no additional questions. So you
Okay,
can move on.
thank you. So I'm now, let me make sure, let's see, maybe there's let me see what sometimes I have to get my arrow on that. I just realized that. Let's see, accelerated fuel. Okay, this is another NEOP. Okay, that I still can address. I forgot to do it. Let's see, this is 2.3. Okay, accelerated fuel development methodology. This is, again, a looking forward type thing. And I'm going to turn this over right away now to my colleague, Ken Keller, who will cover this one and the following one.
All right,
And
thanks.
I'll move forward as he tells me to.
All right, thanks, Frank. And yeah, we can move on to the next slide. Okay, so before I get into some of the text, okay, on accelerated field development, this call is pretty wide open. So you can think physical material things, real world things to accelerate, experimental techniques and such. You can think of new data sources, and you can think of perhaps even using existing data modeling techniques. So just keep in mind this is pretty wide open. So what we're talking about here is trying to take on the challenge of the lengthy qualification process for fuels. So we're looking for any material, any concepts that can accelerate the qualification of fuels. And as these notes say here, we have a range of experiments requiring quantitative integration of disparate data streams collected through the field development life cycle from discovery to deployment. As is written here, historically, data collected during development was used intuitively to mature design as we evolve from technical readiness level to technical readiness level. And the process usually goes from isolated experiments all the way up to prototypic conditions. And the real challenge is prototypic conditions. You'd hate to have to prove that a fuel works in a giant reactor during a bad experiment by having to build a giant reactor and do the bad experiment. We're looking for techniques way earlier than that, through experimentation, interpreting those experiments, and then using modeling and simulation to then envision that big reactor with the bad accident and be able to have confidence to support a fuel design. So accelerated innovation in nuclear fuel technology can be realized by, like, as I said earlier, completing testing tasks more quickly and reliably. Perhaps there'll be a new experiment approach and new test device, and then data related, expanding data streams by looking at maybe relevant features we haven't been looking at before. Some of that relevant information might be sitting in archives. It might be more effective use of existing information from existing experiments. What a good way to accelerate things by not having to do a new experiment, but just look at the information differently. And one key thing we're looking for here is we're interested in process scaling methodologies. By process scaling, we're talking about the one process would be the end state, the real reactor, the real thing we're building, the real machine, the real fuel. And then the other process would be perhaps a very unprototypic experiment. The scaling would be taking this unprototypic experiment, looking at how the material behaves in this non-prototypic way and scaling it to the end state where we want to go. So Frank, you can move on with the slide if you can, please. And this just kind of shows the process scaling. On the left side are the prototypic and questions we have to answer to the regulator and to the owners of the plant. Normal steady state operations, DBAs, design basis accident, which includes reactivity insertions, loss of coolant, or station blackout. And there's also the less extreme abnormal operating occurrences, power ramps, trips, turbine trips and things like that. So the challenge is on the right side, can we take isolated focused experiments, for example, in microstructural evolution, thermomechanical behavior, you know, maybe a simplified thermal hydraulic situation. Look at basic radionuclide transport or other material properties, and can we extrapolate those through modeling and simulation? It'd be great if we could. I mean, the fantasy would be we irradiate something for 5 seconds or 5 minutes, look at how, get a snapshot of how things changed, and then predict the future, you know, for a 18-month old fuel that goes through an experiment. So that's about it. I rushed through that. I'd like to give the floor to Dan Walks. I'm sorry, we do have one more slide here. Okay, here, this goes into some of the specifics on acceleration. One approach, you know, is changing the scale of time and physical dimensions. Now with fuel, we're not too worried about making the fuel smaller for the sake of having it smaller. We can fit it into, generally fit it in. But when you make fuel smaller, you can accelerate burnup. For example, if a fast reactor fuel, if you put it in a thermal reactor, it shields itself and you get a very unprototypic experiment. If you can artificially make the fuel rod much thinner, the neutrons go more across the full rodlet, and you get more of a fast reactor like effect. But there are problems with scaling. For example, if you're going to use the real metal for cladding on your fuel, you probably can't reduce the grain size, you know, or maybe you have manufacturing limits where you'd like to make a cladding very thin to make everything balance out and scale, but maybe you have manufacturing limits where the metal just won't hold up, it's too flimsy, and you can't make something. So those are some of our challenges. But we would really love to scale. Time is the biggest thing we want to scale. Time. Is shorten the time and be able to enhance our extrapolation capabilities. Look at a phenomena and then anticipate the future of it. And down below in the red is just some of the methodologies that have been used. We won't be surprised if we see, you know, these methodologies incorporated in the proposals. And with that, I believe that's about it. And I'd like to give the floor to Dan Walks to amplify or fill in anything he'd like to add.
Thanks, Ken. Yeah, I guess the big thing that I'm looking for here is if we look at historically the approaches that have been taken in the reactor system space to licensing it, developing and licensing an entire reactor system. Obviously, you couldn't build a full-scale plant reliably to do all of your systems testing. It would cost exorbitant amounts of money and take too long. And so since the very early in the 1950s, 60s, we started doing scaled experiments, and a whole body of mathematical engineering processes developed around that scaling process to ensure that the reduced scale or modified scale experiments maintained the proper physical phenomena that were the point of doing the experiments. And so we've seen that be very successful. Many of the advanced reactors that are being deployed now are built, their licensing case is built around doing this kind of scaling. And so what we'd like to do is see that adapted into nuclear fuels. One of the first questions that typically I think about is, why haven't we done this before? Why did the thermal hydraulics community outrace the fuels community by decades in this area? And it primarily comes down to a couple of things. One is access to modeling and simulation tools that can tackle the scale of behaviors that matter to fuel performance. The second is the access to microstructural characterization tools for irradiated fuel. There just hasn't been the data streams to understand what's happening on a material scale like we have today for irradiated materials. And then lastly, the modifications that we're seeing in our irradiation testing infrastructure to be more data intensive, where we're collecting more real-time data that you can use to assess simulations. And so that nexus of things is really changing the world around us, so that we can follow those same kinds of models. And so I'm interested in examples of how we can do that. The FAST experiment that was shown as an example here that Ken mentioned, I think is a good example of that, where we showed that by reducing the diameter of the experiment by a factor of 3 and maintaining the same linear heat generation rates, we accelerate the burnup by a factor of 9 to 10, or a factor of 9. So that means we can take a fuel that's designed to radiate for 10 years and assess end-of-life high burnup phenomena in a year of irradiation. That's a major improvement in the design development life cycle of fuel if we can show that the right phenomena are occurring. There's still a lot of unknowns. So how do the microstructural features in the fuel impact that scaling? We can obviously very easily look at the macro geometry and the thermal conditions and show that they match, but there's some work to be done to show that the material science phenomena do or do not match, and so that we know where the distortions are and where the similarities are. It's also true in looking at, for example, the transient events where it's extremely difficult to simulate an entire loca, for example, whole life cycle loca in our radiation testing facilities. And so what we've historically seen is segmented experiments that look at different pieces of a loca event and try to reconstruct that event from those experiments. And understanding the sequencing of phenomena, understanding the relationships between those phenomena, and where we can make simplifications without affecting the outcomes is important. And so the tools here that are described, hierarchical two-tier scaling and fraction scaling analysis, and now dynamic system scaling, are examples of devices that have been used to execute these methodologies all the way up through licensing. So things that are used by folks at the NRC and other places. So I'm excited to see if we can adapt that to fuels. And again, I'm happy to answer questions. Please contact me if you'd like to discuss.
This is Frank. Before we go on or ask questions, I'm sure there's going to be a question. Are we talking ATF? Are we talking advanced reactors or what? And simplistically, I would say yes, because although clear that advanced reactors, like with metal fuel, is a prime applicant, but there's phenomena that Dan addressed to, like transient evolution. I mean, because of the water reactor, at higher burnup, there's structure within a pin, and there's dopants that we don't know that much about. So I would say it's not that clear, but I say that I've included this as it could have potential to both areas, even though it may be more obvious for metal fuels. But I'm not ruling out. Is that correct? Would you agree, Dan, or is that too much?
No, I totally agree. I think there are near-term applications. I can throw out one looking at RIA performance of LWR fuel, right? So most of the experimental data used by the community right now was collected at the NSRR reactor that had ultra-short pulses. So when we start looking at adapting that data to more prototypic pulses, what phenomena do we keep and what do we lose? I think there are, so you see examples of these things all over the place for fuels. And I would agree, it could be applied to ATF and it could be applied to advanced reactors.
Great, I just wanted to point that out because I think that's an obvious question. I also thought that had relevance in both areas. And now I guess Ken is still in charge.
Okay, the next call is for accelerated fast reactor metal fuel cladding. So what we're looking here is opportunities for significant improvement in a metal-based cladding. So I want to be clear that the focus here is the cladding is a metal. Now you might have non-metal constituents or attributes added or incorporated, but we're looking at metals. And so basically what we'd like to see is proposals that could really give us a jump ahead in where we currently stand with the technologies we're working with. We're looking at a very high dose so we can optimize, so the cladding won't be holding us back for burning up a fuel, that we actually consume the fuel or have reactivity hold us back rather than just the cladding. High temperatures, we get thermal efficiencies, the higher temperature we can operate. So we're always driven to love to have the higher temperatures if possible. And I just want to say, while currently there is a shorter effort to look at fast reactor fuel that is not sodium bonded due to once through concepts where we're concerned with the waste treatment or the storage potential of these fuels. We're not precluding sodium bonding. Sodium bonding is definitely okay. We're okay to see sodium bonded fuel. Sodium bonding is a really great engineering tool that we have in fuel design. So we are definitely still open to that. And so here's some examples to get you nailed in what we're looking for. For example, the ferritic martensitic steel such as HT9 and T91. We have some challenges with, for example, fuel cladding chemical interaction on that. So we're not looking at any, so a viable technique that could significantly add to the lifetime of an HT9 cladding would be interesting. Another area is oxide dispersion strengthened steels, strengthened cladding. There's some real challenges. The oxide dispersion works great in theory. Getting a shape built that we want and installed and manufactured is the real challenge. So that's kind of points you in the direction of ODS where we might want to go. And also new concepts. You got a new alloy, new fuel extension, fuel life extending or cladding extending concept. We're open to them. So let me see what we want to say here. Areas to address in your proposal. So here's a list of areas to address in your proposal. Critical aspects of cladding performance that prevent the particular concept from advancing to a higher technical readiness level. Investigations of irradiation performance, fabrication technology, or composite concepts. So we, although we want this to be metal cladding, we're open to coatings, liners, other techniques, getters, what have you, that supplement a metal cladding. We'd like you to recognize the gaps that need to be overcome and give us an indication of why the concepts you're proposing should be feasible. And it would be helpful if you had a strong knowledge of the current program, the current state of the art of fast reactor cladding. So it would give you a chance to know that you're clearly recommending a significant improvement. And I think that's it for the slides. Frank, I don't think there's another one. So I'd like to offer the floor to Stu Malloy if he's available to add any other details or guidance to applicants.
I think I'm unmuted now. Can you hear me?
Yep.
Yeah. So I think you covered it quite well. I guess the only thing that I would add is just that the present program plan is to actually increase research in this area, but there isn't actually a lot going on right now. So, I mean, I would rely on the fact that there is in the literature there's a large amount of research on the ODS steels as well as HT9. So rely on that for understanding what their limitations are if you're going to propose something to improve those materials, or if you're going to propose something that would be a novel new alloy or a novel new concept. So, other than that, I think that covered it quite well.
Okay, I'll jump in. So obviously this is the type of one where contacting Stu, Ken, or Dan is very important. Just for your entertainment, that picture on the upper right of that's a pre-HT9 FFTF irradiated assembly showing the problem of growth, but exposed to different, it's in a sloped flux region, I suspect. So I know Stu has been working for a long time on ever improving the cladding. So please contact Stu and Ken and others if you're going to propose here, because it's a door to the future that we're trying to make sure we don't ignore. So this is a really, I think, an excellent. It's in the advanced reactor area. Regrettably, we wanted to have more in this area, but if I can tell you, the House and Senate had virtually no funding in this area. So what we do is how we cover it by other methods, like it's a cross-cutting concept, etc. And I think, look, I want to make a pitch for all the other CNIR things. I've looked, when you look at the whole CNI list of everything, I think I see overlaps between what we present and what people that you've heard earlier that you'll hear during these 3 days. There's a lot of interesting relations between different parts of NE that comes out, like in the materials area here. There's some interesting stuff in other areas. So that's something, you know, don't just, if you're interested in this, check all the other ones, even if you hadn't had the time now to look at it over these 3 days. I would just recommend that. I found the CNR document rather interesting reading, which is kind of strange. Let's see, the last slide. Yeah, the last slide gives you the lead contacts for email, and they'll sure set you up. And there's a couple of documents that we put out everywhere. Just I'm on the computer with a group, and I'll call you back later. Bye.
Talk to you later. Bye.
Sorry. I was just going to say, in the referencing, every year we put out an accomplishment report of the entire campaign, and that includes the industry and what's done at the various labs. It's a very nice way to see the overlaps, and we've included 2 years. Dan Walks brought them up, and it's called accomplishment reports, and you can see the evolution over these 3 years. There's so much we're really on a very fast scale of modeling and instruments and our application program. So that's the last thing I'm going to say. I think we have enough time for, I would say, easily 15 or more minutes, but I'd like to open it up now on things that you've heard, particularly the last 2, but then later we can also include everything. So I'd like to ask assistance in opening up if there are any other questions by anybody on the call.
Hi, Frank. We do have a number of questions for the last 2 that were discussed, and if there's more that come in, we'll address those as well. I'm going to try to pull out the FC-5 questions first and lump those together, and then group the 2.3 questions next. The first question is, for FC-5, would high entropy alloys be considered a new cladding concept?
Stu, I'll defer to you.
Yes, yeah, definitely. That's a new alloy concept, so that would fit in here.
Okay, and we have a couple similar questions regarding additive manufactured steels. Would FC-5 be interested in additive manufactured steels or additive manufacturing?
So yeah, I would say we would be interested in it if it does produce a material that has improved radiation tolerance over the present alloys, or HT9 made in the wrought form. Also, if you can use it to make, you need to be able to use it to make a cladding tube. So it can be applied to make it in the shape that we need and make some more radiation tolerant material. Yes.
Okay, thank you. Why is sodium bonding considered a negative in the fuel form?
It's just in waste handling. If there's some storage or waste storage situations where the chemically reactive state of the sodium is undesirable for the waste form. If you're talking advanced fuel where you're recycling it, it's not really a problem. The reprocessors can handle, disassembling the fuel and managing the sodium. So it's a waste form issue if you're going to have once through fuel. And there's some near-term fast reactor concepts. The versatile test reactor, for example, our experimental reactor, as well as some demonstrations that do want to go once through, just use their fast reactor fuel once, and having sodium in them would complicate what we do with the fuel once they're done using it for power.
That's
Student.
correct. I would just like to add to that. What he said is correct, but also when you make the fuel pins, it's an extra step that sometimes can take time. You know, a slug of sodium is entered in it. It has to be liquefied. Then one has to make sure by quality control that it fills up the space and there are no bubbles or gaps. So even though it works very well for the purpose of what it's supposed to do, it would be interesting if we can do away with it.
Okay, thank you. Do you have any examples on coatings and liners?
Dan, you may want to answer that. Wux.
And this is respect to 2.5.
That wasn't
I
specified.
assume,
No, I think it's
okay,
5.
so
It's 5.
yeah, so if we're talking about for fast reactor type applications, if you're integrating a coating into a cladding, there's been quite a bit of R&D looking at, or at least conceptual R&D looking at different coating materials or liner materials. Zirconium and vanadium have been the ones that are most commonly referred to. I think the material choices are not too challenging. I think one of the major questions we have is about application and quality control and the relationship with steels and so forth. I don't know, Stu, if you've thought more about that, or even Nick, I know you've thought about that some.
Yeah, I mean, I think Dan covered it quite well. I mean, it's different. There are present ideas already that that we're looking at already. We're either using a zirconium liner or using a titanium nitride liner or something like that. Something that prevents fuel clad chemical interaction with something like HT9, so that you can go to much higher burnup that we would need for the fast reactor applications.
So this would be one of the areas where it would be very important to try to check in with the experts at the labs who know what's been done, because there has been over many years work on this done. It's certainly open for advanced work, but it's good to get the background on this. If you're going to show, as Stu earlier said, you got to show an improvement, that you're going to come out with something that's better than what we got or considering. Okay, other questions?
Yes, we have additional questions.
Great.
The next one is, would shaping and fabrication of ODS cladding as well as microstructure processing of ODS to improve their properties, would that be of interest?
It would be of interest, once again, if it's going to improve the method of processing it into a thin walled tube form. So, one of the difficulties with ODS alloys is that they're so strong with the fine oxide dispersion that it's processing of it into a thin walled tube form is difficult, especially to the long lengths you need for cladding applications. So if that shaping technology helps you get there better than, say, pilger processing, which is one of the leading technologies now for ODS steels, then yeah, that would be applicable to this call.
Next question, for FC-5, what kind of TRL is needed for the materials?
I don't know if Ken wants to answer that, or I'll answer that. I mean, it's there's a range of TRLs that we'll be looking at, for these materials. So if you're enhancing ferritic martensitic steel, or you're enhancing an ODS steel, then you may be at the higher TRL levels of 4 to 5. But if you're just proposing a novel new concept, then it may be at the lower TRL 3 to 2 to 3 levels. So I think it really depends on what the concept is that you're proposing as to what TRL level it is.
Stu, I would only
Yeah,
add.
I would say that.
Oh, go ahead, Dan.
Oh, go ahead, Ken. All right. I was just going to say, I think one of the key things is to be cognizant of the TRL level your concept is at when you make a proposal. and to be addressing the kinds of questions that are appropriate for that TRL level. That's all I had to say there, Ken. Go ahead.
Okay, and I was just going to layer on, we certainly don't want someone to dial in on one phenomena of fuel and say this thing, we want the proposer to be aware of the full life cycle demands of this cladding. You know, getting the material, can you find it in nature, manufacturing it to the shape, like Stu pointed out, the shape, normal operating conditions, the chemistry. We don't want someone to say, hey, that's one phenomena of cracking in this situation, this will address it. Make sure that what you're proposing, you're considering the full life cycle, so that you've demonstrated to us you understand the full environment that this cladding is going to be in, and that you've considered that at least with the information you have available, it's a viable in all aspects of the life of the cladding.
Okay, the next question for FC-5. Would there be any interest in including modeling, or is the focus purely on experimental-based proposals?
Good question.
I would say in general, the focus is mostly, in this case, on experimental-based proposals. Yeah, I think for this proposal, I don't see significant addition of modeling to it would help. So.
Okay, thank you. We have a set of questions for FC 2.3. The first of those is the focus of FC 2.3 on LWRs?
I think Frank asked that question, right? And said we're really open to acceleration of any fuel, any new fuel concept of accelerating it and getting it licensed as fast as possible. Dan, do you want to amplify on that?
Okay, I was thinking 2.3 was the accident tolerant control runs. But yeah, I think if it's the accelerated fuel cost methodology, I think that examples of opportunities to apply these kind of techniques to ATF or LWR applications, will certainly resonate, either more with our mainline programs. But I wouldn't constrain it to that. I do think there's advantage to some of that route, though. But we would certainly entertain good ideas in both advanced reactor and LWR.
Oh, and by the way, we can't go back in time and accelerate the qualification of existing ATFs that have already gone through that process, right? So let's not waste time on some of the.
Yeah, there may be some advantage to doing a mixture of demonstrating methodology with known data. But I do think it's important to take forward-looking, to be forward-looking in how we'd apply it to next generation technologies. I agree with you, Ken. I don't think.
I'm sorry for the interrupting, but I would add there are questions LWR that we haven't answered. Okay, so
that's correct.
What Dan says is relevant. Sorry for the interruption.
No, I agree. That's a very important point, Frank. I agree.
Thank you.
Yeah.
Okay, for FC 2.3, would any irradiation test be encouraged, such as ion irradiation or neutron irradiation?
I think in this particular case, we would be, this is a small project, right? So it's an 800K type of NEUP. So it's probably beyond the means of the project to generate much new data. I think the emphasis should be on cases where we can identify existing data and use it to develop the methodologies for analysis of the data as opposed to generating new data. There may be cases where there are small gaps or simple experiments that could be run to demonstrate principles. I wouldn't be against that, but I would rather see the emphasis placed on the methodology development and validation over over data generation.
Hey, Dan, Ken here. On the ion irradiation, maybe I'm off on the state of the art of it, but there's still a lot of I think uncertainty in the prototypic aspects of it, and you know that there's always that some region of your sample that's looking pretty good, but then other regions. Would there be any value in improving the data interpretation or confidence of an ion irradiated sample and scaling it to a neutron irradiation?
Yeah, that's exactly one of the places I think that there may be some opportunity here, is to use some of these scaling methodologies to identify the dominant physics and formally connect those dots, and see, what things are working with ion irradiation and which things do we actually need neutron irradiation to capture.
Okay.
Again, I think in that area, as Stu has said elsewhere, you have to show that you're improving, because there is a lot of ion irradiation data and it's being used. The question is there a concept which would use it in a different way that would make it easier to use it as a scaling concept or so? So it's a challenging area.
I agree.
Okay.
Okay, the next question is for FC 2.3 again, and again involving ion irradiation. So would ion irradiation experiments be considered as a possible source of accelerated irradiation data?
Again, I think it's the same answer in that case. I think it's possible that ion irradiations could be used in that way. But as I said, I think the goal here is the mathematical connection between those two things. I don't want to. I would not be interested in ion irradiations being funded under this project. I think it would be studying the relationship between neutron and ion irradiations to try to quantify the connection between the two.
Yeah, it already is an excellent example of an acceleration concept, okay? But its use is difficult. So if something would show how to make it easier or faster or more accurately to use, that might be a question. But clearly, it's a field that's already heavily, investigated and used. Okay.
Okay, next question. For FC 2.3, would a project focused on modeling and processing existing data with no new experiments, would that be considered?
Yes, I'd say that's very much what we're looking for. That's what I'm interested in. Is if you have existing data and we can use that, use these tools to kind of assess the relationship between data sets, that would be ideal. Modeling works. These kind of tools are great for pursuing validation of models and also extrapolation of data and models. So I think that's a pretty good fit.
Okay, we have a couple more questions dealing with FC-5. So for FC-5, would you request to perform experimental tests to meet the 3 design conditions, particularly high-dose irradiation tests?
I mean, I wouldn't say you have to meet, I guess, all of the 3 design conditions, but particularly the higher dose is the one that you want to, I think, aim for these new material concepts or improvements in material alloys. And of course, the only way you're going to be able to do that is through ion radiation. If you go back to the other questions, but in this case, to those such high doses, you're not going to get there with reactor radiation. Not on these proposals.
Okay, thank you. The next question, for the processing method to apply cladding, are we seeking for a technique to lower the cost?
Which one are you talking about? Can you say the FC, which one?
It's not specified.
Oh,
I mean, if it's related to FC-5, I would say no. We're not looking for a cost savings here.
And if it's related to accident tolerant fuels, again, it would have to be relevant to something that's existing.
The only thing I'd add is if someone's proposing additive manufacturing for cladding, that has the potential of being really slow and costly. And so there, if additive manufacturing is pushed, the reality of, could you really make a lot of cladding with this thing in a realistic time should be addressed. So in that subset of information, I would say cost would be important. I don't know, Stu, do you have a different angle on that?
I mean, yeah, cost is important in this, but I mean, the main thing we're aiming for is showing material that has improved radiation tolerance under these design conditions. So if it happens to be more expensive to make that material, that isn't as much of the issue as being able to actually address these challenging conditions. So.
Yeah, good point, Stu. I kind of retract my statement because, like, ODS is such a promising thing, and it seems to be really hard to make. So, yeah. So if we could just make so good point. So if we can make a breakthrough and have a cladding shape in ODS that works well, like, forget the cost for a while. Let's play with this and see if we got, and then we'll address the cost, right? You wouldn't want to throw it out with the bathwater, as they say.
Right.
The next question is for FC-5. Why is the temperature of 700 degrees Celsius plus prescribed?
Stu, I'll leave that to you.
Yeah, so I mean, I think the only reason why we pointed out being able to go to even higher temperatures is for more efficient reactor applications. But I mean, to be honest, for the main application, the maximum temperature is not going to get, for example, a sodium cooled fast reactor is not going to get to much higher than 700 C, just because designing a reactor to such a high temperature is extremely challenging. So, but I guess what we were trying to say here is that improved properties at higher temperatures is an advantage that we're looking for. Take HT9 for example. It has a significant reduction in mechanical properties as well as creep strength at high temperatures above 600 degrees C. So a material that actually shows some improvement in that temperature range is one that we would be looking toward if it also meets some of the other requirements, such as the high dose requirements needed for this application.
Okay, thank you. The next question for the advanced fuels topics, is a novel manufacturing method for TRISO fuels of interest?
This is Frank. No, I think I rule that out because we say accident tolerant fuels. It is in its own way certainly an accident tolerant food, but we're talking about the accident tolerant fuel program with the existing 3 vendors. It's a fascinating question because clearly it is but I would exclude it from consideration in these NEUPs.
Thank you, Frank. And I have one more question, and it jumps back to FC 2.2, and this may have been asked earlier. But the question is this control rod project focused on modeling, experiment, or is it better to combine both?
Mike, are you still on?
Yes, I am.
Great.
I think if possible, elements of both would be valuable.
Okay, thank you. There are well, as I said that, another question just came in. This question deals with FC-5. While designing a new cladding, are there any particular targeted properties prescribed? For example, creep, segregation, and corrosion?
I would just go back to the sort of the last part of the areas to address in your proposal. So I think you want to look at the present gaps for the leading materials like ferritic martensitic steels or oxide dispersion strengthened steels, and then address those in your proposal. So I'm not saying that I'm aiming for one or the other, whether it's segregation or swelling or something like that. But I think that you look at the gaps that we have for using a material like the present HT9 out to 300 DPA and address that in improving that material so that you have a better material to be used in those conditions.
Okay, thank you. And at this time, we have no more questions. Thank you all for the presentation and answering those questions. Frank, did you have any concluding remarks?
Yeah, I first want to thank everybody. First, the people who've worked on it, the technical people who proposed these concepts, Dan Wachs, the other people at headquarters who were involved, beside Ken, myself, our supervisors. I mean, there's a lot of work on this. And regrettably, I have to warn everybody that there still is a serious budget uncertainty hanging over our heads. We have been optimistic in proposing these, and we hope there's enough money to do several, but it is a possibility that there's going to be only a few concepts pursued. And that's another thing I always want to say. If you come in with a letter of interest and you're not encouraged, or you come in with a formal proposal and it's turned down, a lot of times it's the budget limitation that causes us not to pursue something, not that it isn't a pretty decent idea. So keep that in mind. And that's why I say try to focus in and try to keep in touch with the technical points of contacts so that you have a chance of getting a good response, because there will be a lot of good ideas. It's just that we in this area are pretty constrained. But we wanted to change. For the last couple of years, we've been criticized for doing less in NEOPs. And I think the criticism has been valid. The reason that caused the criticism a couple of years ago was, again, a budget issue. And so I hope at least the university participants who are on this call, and I want to thank you all for bearing with us. You're really the target audience, okay, with the NEOP effort and even the IRPs. So we're hoping that you'll see that we have an intent of doing more with the universities than we have in the past few years. And this is an evidence of it. But again, you may find out that we can't do nearly as much as we'd like to. So again, take that in mind when you get comments. They're not all absolute why it was great or not great. Well, in that sense, to say I thank everybody. I thank the NEOP folks who helped set this up and minimize the problems that people such as me can cause when we don't use that experience. I think it worked very well. I thank you all. I guess, Dan Wachs, you want to also maybe say something?
Yeah, I think the big thing I wanted to highlight is this is a substantial part of the Advanced Fuels Campaign budget that we're wanting to engage with the university community in supporting the program, and I think that you've heard it expressed in many of the calls here that we're very strongly encouraging collaboration and discussion. We want you to be a part of the program. And we're hoping to be deeply engaged in the work and making sure that it gets the full credit and impact it can have on the program. So please engage your technical point of contact early in the development of your proposal and thinking about your ideas. If you need help identifying people in industry to contact and discuss ideas with, please don't be shy about asking for some help with that. We do have a handful of contacts, and we want to help you make the best ones you can. So looking forward to what comes down the pipe, and hopeful that the budget allows us to support this at the level that it needs to be supported at. But there's some water to go under the bridge for that. So happy to help in any way we can. And that's all I had, really, Frank.
Thank you, Dan. I appreciate that. And again, I appreciate all the technical POCs. And there were some who we had to drop. I apologize we dropped a couple of areas. I apologize for the work TOPs in that area did, but we try our best. Thank you all.